Okay, Matthew Fickus is a professor of mathematics at the Air Force Institute of Technology. He received his PhD from the University of Maryland in 2001 under the direction of John Benedetto. And over the last 2 decades, Professor Fickus has become a leader in the field of frame theory. He introduced many fundamental concepts in the community, including the frame potential, spectral tetras, and eigensteps. In recent years, his research is focused on the construction of equiangular tight frames using tools from combinatorial design. Today, Professor Fickus will speak about one of the latest developments in this body of work. Take it away, Matt.
Thank you, Joey. Thanks to all the organizers. Thanks for all of you for coming. So yes, this is work with my PhD student, Ben Mayo. And I want to start off just motivating with some general work about what we call projective codes. And before we get to there, I'm going to talk about something even simpler called spherical codes. So this is Thomas's problem from 1930. The idea is we want to pack points on spheres in a particularly efficient way. In particular, I'm going to try to pack n points, unit vectors, on the unit sphere in RD, so that they maximize the minimum distance between any pair of points. So that basically they're as far away from each other as possible. Now there's an alternative way to think about this. You can take this Euclidean norm, write it as its dot product with itself, because every vector has length 1, it reduces to this. So instead of trying to maximize the minimum distance between any pair of points, because of that minus sign that shows up right here, that actually, instead of maximizing a minimum distance, turns into minimizing a maximum dot product between the two. And here are some solutions to this problem. These are optimal packings of n points on the sphere in R3 on S2. So if I want to pack 2 points, and this makes sense, I just put them as opposite points, like North Pole, South Pole, one point on the equator, opposite point on the equator. If I want to pack 3 points, I do 3 equally spaced points around the equator. If I want to pack 4 points, I want to pick the vertices of a tetrahedron. And you might notice something going on here. All 3 of these examples are what we call regular simplices. The last example is actually the regular simplex of 4 vectors in 3-dimensional space, the regular 3 simplex. Well, the previous one is actually the regular simplex in a 2-dimensional subspace of R3, and the previous one is like a degenerate simplex, a simplex of 2 vectors in 1-dimensional space. If I want to go past that, if I want to pack 5 or 6 points, I can't use a regular simplex anymore because I can't fit one in 3-dimensional space. And what it turns out I can do in that case for 6 points is take something that's called an orthoplex, which is the standard basis union the negative of those elements. And it turns out that that's also the best I can basically do if I want to pack 5 points on the sphere, is this arrangement here. Take one of those and throw that away. You can actually prove this stuff I was just saying. This is related to what Rankin proved in 1955. When the number of points is no more than 1 more the dimension of your space, optimal spherical codes, optimal packings of n points on the sphere in RD is exactly the same as regular simplices. And the proof is actually pretty simple. It's right here. What you do is you sum the vectors and you say, well, whatever that is, it's a vector, and so it has a non-negative norm. You write that out as a dot product of that sum with itself. You distribute all the cross terms. All the diagonal terms in this sum are 1 because all the vectors have length 1. And then all the off-diagonal terms are less than or equal to their maximum. And then you could, move the n over to the other side, divide both sides by n, and you get a lower bound on the maximum inner product. And when is that going to be achieved? Well, it's only going to be achieved if both of these inequalities in here are equalities, which means you need a bunch of vectors that sum to 0. And you also need that all of the off-diagonal inner products here, the inner products with different indices, are all equal to each other. And it turns out that that completely characterizes a regular simplex. And so you can actually prove formally in this case that that's the optimal packing. When you go beyond that, when you have more than d+1 points, it gets a little more difficult. But what you can actually prove, and this makes some sense geometrically if you think about it, if you pick n points in RD and n's greater than or equal to d+2, you can't make them all obtuse. at least two of those vectors have to have a non-negative inner product. And that's exactly what we're saying here. And this is actually achievable as long as n is less than or equal to 2D, because you can pick the arrangement to be the orthoplex. The proof is much less obvious if you had a bunch of mutually obtuse vectors and you can project all but one of them onto the orthogonal complement of the remaining one. And that actually produces one less mutually obtuse vectors in one less dimension space. And you keep walking this back down until you get a bunch of mutually obtuse vectors in R1. And so you have a bunch of scalars where the dot products of any pair of them are negative. And so you can have at most two of those. So that's the argument here. Okay, so these are just packings on how to optimally pack points on spheres, spherical codes. This talk is more going to be about constructing what we call projective packings, which are going to be in projective space. And in projective space, what you do is you take a Euclidean space like RD or CD, which we're going to have as FD here. And we're not actually looking at points in that space, but rather lines through that space, one-dimensional subspaces, lines that pass through the origin. And there's various ways to write them down, but we're actually going to associate each one with the outer product of a unit vector in FD. That's one way to kind of write them. Obviously, if you replace a unit vector with a unimodular scalar times itself, this guy's not going to change. The reason we like to write it that way is because it does suggest a natural norm on that space. We want to pack lines, and so we need a notion of distance between lines. And these rank 1 projections, phi star, they're all living in this space of self-adjoint operators, which is a real inner product space under the Frobenius inner product. And actually, if you take the Frobenius inner product of two such outer products, sorry, I'm using my mouse both to highlight and also advances, to be a little more careful, then what you can do is write that out as a trace, cycle the trace, and then you actually end up with the inner product modulus squared of the original guys. And so when you take the Frobenius distance between two such projections, very similar to the argument we did before, but what you get is this quantity, which is noticeably different than what we had before, because before we did not have an absolute value, and now we do. And so what this leads to is, if you want to optimally pack n lines in FD, in other words, arrange them so that the minimum distance between any pair of the projections onto those lines is as large as possible, then it turns out that you are exactly trying to find a collection of unit norm vectors that have minimal coherence. In other words, so that the inner product of any two distinct vectors is, well, when you take all of them, take the largest one of those in modulus. That modulus is important. We're trying to minimize that particular quantity. So if I didn't have these absolute values here, I'd be doing sphere packing. But because I have these absolute values here, I'm doing projective packing instead. And it makes a big difference because, for example, if you want to pack 3 points on the sphere in R3, you pack them to be the 3 equally spaced points around the equator. When if you want to pack 3 lines in R3, you make them all mutually orthogonal. You make them be, for instance, the lines generated by the standard basis. Another way of thinking about this problem, just sort of as a matrix design problem, is I want to make this short, fat matrix, D by N. So D is the number of rows, the dimension of space, and N is the number of columns, is the number of vectors I have. So that when you take its Gram matrix, that which computes all the inner products between these vectors, you're going to have ones along the diagonal because I'm assuming they all are unit norm. But on the off diagonal, I'm trying to make the largest off diagonal entry in modulus as small as possible. So it's like I'm taking an infinity norm of the off diagonal and trying to push that down as much as possible. And so that's what I want to do. I want to find vectors of minimal coherence. I want to have this design problem. Now, why care? Well, for both of these problems, there is a ton of sort of related, really important classical problems out there. I view the problems that I'm going to be doing here as sort of a mathematical abstraction and unification of a number of things. And I'm going to be talking more about projective codes and spherical codes. But even spherical codes, and that's classical, especially very applied, a lot of algebraic coding theory, error correcting codes, error detecting codes, comes into trying to design exactly that, where the actual real vectors have +1s and -1s in them. They are obtained by exponentiating binary code, raising -1 to the binary power. But like projective codes, trying to find things of minimal coherence, we have been trying to minimize coherence as a society for at least like 80 years. Right? So, and lots of things involving continuous waveform design, things about for radar, sonar, communication. We often try to design libraries so that, for instance, one member of a library is incoherent with translates of itself. That's the classical ping from sonar, right? I'm going to send out a pulse, and it's not going to look much like itself unless it's shifted to be itself, okay? As opposed to if I had a sine wave and I translated it, it looks a lot like itself. It coheres a lot with itself. A lot of times in radar, what we want is something that actually is very incoherent with its own translates and modulates, because that's exactly the type of stuff that's going to come up when we send a radar out. It bounces off a target. Maybe the target's moving, and so there's a Doppler effect, and it shifts its frequency. But it also gets shifted in time because it had to fly out to the target and then fly back. So we want functions that are incoherent with their own translates and modulates. That's what the ambiguity function measures, and things like chirps are popular things because they have nice ambiguity functions, close to being perfect thumbtacks. And then, I mean, those themselves are classical. Even going back in the last few decades with the rise of wireless communications, OFDM, CDMA, all these things, we're trying to design like nice libraries of stuff with small coherence. Now, the term coherence has really risen in popularity with compressed sensing. Okay, so there's a bunch of stuff there. I'm not going to go into the details of them. We know there's actually more going on there. There's RIP. We might like low coherence is necessary, but often is not sufficient for RIP on the order of random matrices. This stuff also arises in certain applications involving quantum tomography. That's a little bit harder to see. We'll be talking about that more as the day goes on. But here we're actually trying to recover a self-adjoint matrix by taking the matrix and hitting it on the left and right with a vector and its transpose. You can actually write that as a Frobenius inner product of A with the outer products of those guys. And remember that the coherence of the outer products is related to the coherence of the original vector, so they're related to each other. Also in statistics, in design of experiments, looking through that literature, they also, and I know some people in that literature and talk to them, and it's like, yep, we're trying to design really nice short fat matrices where all the entries of those matrices are plus or minus ones and all the columns are orthogonal to the all ones vector. So this minimizing coherence thing comes up in a lot of places. And and by analogy, you know, when you study something like algebraic topology, or algebraic geometry more precisely, it's like systems of polynomial equations show up everywhere. And an algebraic geometry says a lot, or says a little about a lot of problems, even more precisely. And it's like coherence comes up everywhere. And what we're doing here with trying to design things with optimally small coherence is say a little about a lot of problems, trying to study an idealized version of this very practical problem that shows up in a lot of places. So you could try to then relate these two problems together to solve them. You can say, hey, Rankin has this idea that I, in certain special cases, can actually solve this optimal sphere packing problem, or packing on the sphere problem, the optimal spherical code problem. And I can try to turn the optimal projective packing into an optimal sphere packing problem. And so what we can do is say, hey, remember, since the inner product of the outer products is just the modulus squared of the original one, I can think about this mapping where I take any column vector d by 1 and I assign a vector in the space of all self-adjoint operators by taking its outer product with itself. And that space is itself a Euclidean space, and its dimension varies based upon whether the underlying field is real or complex. Either way, this is a real space, but its real dimension is based upon whether the underlying field is real or complex. And so we could say, hey, if you had some phi-n's and you lifted them, as we say, to some corresponding xn's, if those guys happen to form an optimal spherical code, then the phi-n's would happen to form an optimal projective code. The problem is that it's never going to be in this particular case. And Bernard brought this up very nicely in his talk a few weeks ago. And it has to do with the fact that when you lift in this particular way, all of these rank 1 projections are all on the positive semi-definite cone. So they're all in the same corner of space. And because they're not allowed to be spaced out, they can't form an optimal spherical code. That said, this does lead to something that's going to come up a number of times in this talk. In the case of equiangular lines, this becomes something called the Gerson bound. Here I'm going to just phrase it as what's called the proto-Gerson bound. And what it says is, hey, if you give me any unit norm vectors in FD, I can lift them to their rank 1 projections, and I can talk about what the rank of those rank 1 projections, what's the dimension of their span. And in general, that's what I'm talking about here. And that's the same thing as the rank of their gram matrix, but their gram matrix is the pointwise modulus squared of the gram matrix of the original vectors. But regardless, they are vectors living in this real space of self-adjoint operators. So you get these bounds based upon the dimension of the space that they're in. I mean, a bunch of vectors, the dimension of their span can only be at most the dimension of the entire space. Now, when will they achieve equality in this bound? Well, they're going to achieve equality in this bound if and only if the outer products of the phi-n's span that entire self-adjoint space. So equality holds saying that they themselves form what we would call a frame or spanning set for that space. And what that means is if you get equality in this sort of proto-Gerson bound, that means that you can recover any self-adjoint A from measurements of this form. In other words, you can successfully perform quantum tomography. Okay, so Conway Hardin and Sloane have a very nice and important nuance on this. Instead of just trying to map a vector phi to its outer product with itself, we take the projection of that onto the orthogonal complement of the identity matrix. In other words, we make the operator traceless. We make it have trace 0. And then we do this thing, which is going to turn out to be a renormalization step. These things are no longer living in the entire space of self-adjointed matrices. They are living in a subspace of it of codimension 1, the subspace that has trace 0. And it turns out that when you do that, you still have this nice sort of isometric-like relationship between what the Frobenius inner product of the lifted things are and what the original guys are. The important thing is what this does geometrically is whereas before all your outer products were sort of confined to this corner of space, they are no longer required to be so. And so it turns out that under very careful choices of the phi-n's, these xn's can sometimes turn out to be simplices and other times turn out to be things that meet the orthoplex bound. And so can turn out to be things that can meet Rankin's spherical code bounds. And in that case, when you think about it, what that actually implies is that you're going to get an optimal projective packet in that case. In other words, a sequence of vectors of minimal coherence. So this talk is going to focus on 2 specific types of those. Equiangular tight frames are going to be things that lift to simplices, and mutually unbiased bases are going to be things that in a certain case are going to lift to something that meets the orthoplex bound. So the Welch bound, which was actually, if you read carefully, also discovered by Rankin. This is not the paper of Rankin I was mentioning earlier. It actually came 1 year later, and he was studying quadratic forms. But if you dig into some results at the very end of that paper, you see Welch's bound is actually in there, but then also Welch, and also discovered by Conway Hardin and Sloane. The Welch bound is an instance of what they call the simplex bound. And what it says is, hey, you give me n unit vectors in FD, the coherence of those vectors is bounded below by this kind of ugly looking number. And equality holds, well, equality holds, it turns out, if and only if the lifted version of these phi-n's, Conway Hardin and Sloane's lifted version, forms a regular simplex. And what that turns out to be is that these phi-n's have to be what we in frame theory would call an equiangular tight frame of n vectors in d-dimensional space. And that actually consists of 2 points. First is a tightness condition. And what we call this is the frame operator right here. And that is actually computing the inner products of the rows of this matrix. So these are not the inner products of the frame vectors with each other. It's something else. I'm going to have some examples in just a minute. But it's saying there's some sort of orthogonality, but not with the vectors themselves, something else in the coordinates of those vectors. And then the second part is you need this equiangularity condition, which says, hey, we're trying to design matrices so that the off-diagonal entries of the gram matrix, the largest one of those is as small as possible. Well, in order to achieve equality in this bound, they actually all need to be equal to each other. Now, what they're equal to is exactly this Welch bound up here, but they all need to be equal to each other. when you take that proto-Gerson bound and apply it in this case, the equiangularity condition actually ensures that you can compute the rank of the pointwise modulus squared of the gram matrix of the phis explicitly. And it turns out to be n. And so what you get in here is this bound, which says, hey, if you want an ETF, you can't have too many vectors. The number of vectors has to be on the order of the square of the dimensions, because else it won't be able to form a simplex after you lift it. So here's some small examples. I'm going to work a lot with examples in three-dimensional space. If you want an ETF of 4 vectors in three-dimensional space, 4 lines in three-dimensional space, it turns out it's the same as the packing of 4 points in three-dimensional space. You can pick the vertices of the tetrahedron. And so I have those vectors arranged as the columns of this matrix here. And what I'm doing to the right is verifying the ETF conditions. One is the tightness. So it's when you take phi star, which is computing the inner products of the rows of this matrix with each other, that you get a constant multiple of the identity. So it's interesting, in order to make the columns sort of as orthonormal as possible, in the sense that they meet the Welch bounds, you actually have to design the rows to be exactly equal norm orthogonal, okay? In this particular case, again, to achieve equality in the Welch bound. And meanwhile, when you look at the gram matrix itself, you get ones along the diagonal. There's the scale factor of 1/3 out front. And then on the off diagonal, you're getting all entries of equal modulus, because in this case, they happen to all be equal. A more interesting example is, by the way, there is no ETF of 5 vectors in R3. There is one of 6 in R3. And I'm not going to tell you the vectors themselves as a formula because they're kind of ugly. But what you do is you take the icosahedron, which has 12 vertices, and those are arranged in terms of antipodes, right? For each one, you get its negative. From each one, pick one out of those 2. So you can almost take like a single point and then go down to a certain line of latitude, so to speak, pick 5 equally spaced points around them. The lines passing through those points for the right latitude will actually form the vertices of an icosahedron. And notice that when you take inner products of the rows between that, you get a constant multiple of the identity. And when you take inner products of the columns, you get ones along the diagonal. There's an identity here. On the off diagonal, you get the same value up to a modulus. So it's an ETF. So that gives you an optimal packing of 6 lines in R3. Now, it turns out if you want to do a real packing of lines in R3, that's the most you can do, because that's what Gerson maxes out at. But if you want to go complex, you can get a little bit bigger. You can find an optimal packing of 7 lines in 3-dimensional complex space. And the way you actually do it, and this will be related to some stuff that's coming up, is you take a 7x7 discrete Fourier transform matrix, or as I've written it actually here, the character table of the group Z mod 7. And you pull out 3 rows of it very carefully. The 3 rows have to correspond to what's called a difference set, getting into that a little bit later. And when you do that, well, the entire character table, all of its rows were equal norm orthogonal. So if you pull out a few rows of it, they still have that property. But what's remarkable is that we've pulled out the right 3 rows here, so that when we take the gram matrix, which is the 7x7 guy, all the off-diagonal entries have the same modulus. It turns out that the values in this case are a number or its conjugate, or that's this particular number here. And just trying to give you examples of these so you kind of get an idea of giving you, these examples are actually all prototypes of stuff that has been generalized. Here's the most you can do in the complex scenario, that in the complex setting. If you want to pack 9 lines optimally in 3-dimensional space, which is an example of the SIC-POVM, meeting Gerson's bound in the complex case, the maximum number of equiangular lines you could have there, you can do this particular construction. This construction, I was fortunate enough to be studying unit norm tight frames and equiangular tight frames back like in 2003 or so. And I got an email from Joe Rennes very early on, and he's like, hey, can you guys build this? We're looking for things like this. And that started a lifelong obsession with SIC-POVMs myself. I'm not as much of a junkie as I know some of you out there are, but I'm still really interested in it. And this particular example here, when you look at it and you kind of compare it to some of the stuff that Seidel did in the 70s, you can very easily see stuff that Dustin, Janet Tremaine, and I did later on, where we're like, yeah, that Steiner construction, the Steiner ETF construction, that is implicit in Goethals and Seidel's construction of the 70s is also represented here. It also works in the complex case. And the quantum people were nice enough to share this example with me very early on. And what you actually see here is you're actually taking 2 by 3 simplices, embedding them up into 3-dimensional space by like tacking a row of zeros onto them 3 different ways. And here's some magic happens where, you know, within each kind of group of these things, grouping of these things, you get like a little grand matrix of a simplex. But cross groups, there's only one point of interaction. And so you're still getting a unimodular. So, so from this, you might be like, oh, there's lots of ETFs out there. Well, they're actually they seem to be rare, but we don't really know that for certain. In particular, in the complex case, we have very few sort of necessary conditions upon their existence. And so if you went up to even dimension 4 and started asking questions about complex ETF existence, we would all very quickly get to points where we don't know what the answer is in this case. And that's part of what this whole talk is geared to, is like, well, one way to figure out the existence problem is try to construct more ETFs. And that's eventually what I'll be delivering for you as we get closer to the end of this talk. Another bound, so I'm segueing away from ETFs and starting to segue towards mutually unbiased bases. But I got to talk about something else to begin with. If you're beyond the Gerson bound, then you cannot have your lifted versions of your phi-n's form a simplex, because there isn't enough space up in that self-adjoint space for that to happen. But instead, you could ask, well, is it possible that my lifted versions of my vectors meet what Rankin called as orthoplex bound? And so we could ask that question here, and what it turns out is that the coherence of this number of vectors in this beyond the Gerson range is at least this number 1 over root t. And it's fascinating that number does not depend upon n. If you achieve equality there, you get what's called an orthoplectic Grassmannian frame. It turns out to achieve equality there, you do have to be a frame, but you do not have to be a tight frame. And in particular, if you achieve equality there, you could throw away one vector from it as long as you stayed in the beyond Gerson range, and you would still meet that bound because it doesn't depend upon n. There are some really pretty examples of these OGFs from a recent paper of Bernard and John Haas. And some examples here, even in the real case, is to like take that regular simplex of 4 vectors in 3-dimensional space and sort of adjoin the standard basis to it. And here you are beyond the Gerson range because you can have at most 6 equiangular vectors in real 3-dimensional space. And so you're one more than you absolutely need to have. This turns out to be a tight frame, and this also turns out to have minimal coherence, so it's pretty great. And in the complex case, you can do an analogous thing, take the 3 by 7 ETF and stick this standard basis on it, and you get a orthoplectic Grassmannian frame of 10 vectors in 3 dimensions. I think this is not advertised enough when talking about SIC-POVMs. For a SIC-POVM, we would be seeking 9 vectors in C3. And we know how to do that, but with SIC-POVMs, we only have a finite number of examples of them. Meanwhile, this construction of Bodman and Haas, it turns out that what we kind of have down here, there are literally an known infinite number of these. You take a harmonic ETF coming from a Singer difference set and then attach a standard basis to it. And what it gives you, it turns out, is it lets you do, at least from a mathematical point of view, lets you do tomographic reconstruction. And it also has minimal coherence. The cost is you need to take one more measurement than absolutely necessary. But from my perspective, that makes the SIC-POVM, even more beautiful, but more of an academic problem. It truly is, the crack cocaine of our area, where it's like, I have no practical reason from my perspective, a physicist might be able to correct me, to actually look for them in light of these other constructions. I would like to actually have a reason, but it doesn't stop me from going after it because they're just too beautiful to not seek. All right. I promise the organizers that'll be the most controversial thing I'll say in here, the references to crack cocaine. All right. I am in a not paid status from the Air Force right now. I'm on my summer break. So I'm not going to say anything too stupid, but I'll say that. Mutually unbiased bases. So what we're going to do here is we're going to take a collection of orthonormal bases for the same space. They're bases for the entire space. but we're going to require that the inner products of any member of one basis with any other member of the second basis all have constant modulus of inner product. And so an example here is to take the standard basis in R2 and union it up with taking the standard basis and rotating it by 45 degrees. Each one of these is an orthonormal basis for R2, but if you take a dot product of any member of one basis with any member of the other one, you get a constant inner product, and it turns out the constant has to be 1 over root d. A similar thing here, you can actually find 4 mutually unbiased orthonormal bases for 3-dimensional space. And the first 3 are actually pretty nice. They all kind of look very Fourier-like, but they're not. They actually come from, well, there's various ways to construct them, but there's a Fourier chirp construction. There's also a different set related construction for them that I'll be talking about later on. But you can basically get these 3 by 9 and chuck the standard basis on it. It turns out, if you look at what the proto-Gerson-bound says in that scenario, that if you're trying to construct M mutually unbiased bases in d-dimensional space, there's a limit on how many of them you can make. You can have at most d plus 1 in the complex setting and at most d over 2 plus 1 in the real setting. If you do achieve equality here, if you have a maximal MUB, as we will call it, then you can prove that you actually meet the orthoplex bound, that you are moreover beyond the Gerson range. And so you are an orthoplectic Grassmannian frame. You have minimal coherence. And moreover, you can prove that it actually enables you to do tomographic reconstruction. And so you see a lot about MUBs in the quantum information-theoretic literature. All right. So before moving on to the new stuff, I just want to advertise the areas more broadly and say there's still lots of really important open problems here. Like, when does an ETF exist? Zahner's conjecture that there always is going to be a complex ETF of d-squared vectors in d-dimensional space. It's always going to be a SIC-POVM of that size. That's still open. More generally, we just are sorely lacking necessary integrality conditions on complex ETFs. We have pretty strong ones, though not perfect, on real ETFs that come from a connection to strongly regular graphs. It is interesting that it has been proven with algebraic geometry that a complex ETF 3x8 does not exist. And I have made a conjecture based purely on experimental observations that for every known ETF dn, that you take these 3 particular parameters, and it turns out that one of these numbers divides the product of the other 2 from a purely experimental perspective. And I have just conjectured that that is always true. Now, to go on the record, I don't know if I believe that conjecture or not. So you might not want to call it a conjecture, but certainly as a problem, that would be a problem I'd be really interested in knowing the answer to. Similarly, there's some really exciting open questions about MUBs. There are, I didn't on the ETFs show all the known constructions, but for MUBs, you can actually find maximal ones for any prime power Q. And actually, as long as the Q is a power of 4, you can find real maximum ones. Moreover, there are other constructions of them. There's a tensor product construction of them that's kind of analogous to the tensor product construction of mutually orthogonal Latin squares. And moreover, there's a direct construction of MUBs from mutually orthogonal Latin squares. But even in dimension 6, we can form 2 MUBs pretty easily. Just take the identity and the Fourier matrix. But beyond that, I think we're open from whether there's 3, 4, 5, 6, 7. Of course, if there's 5 of them, there's also 4. But even just knowing if there were 3 would be a nice thing. I don't know this literature nearly as well as I should, but my impression of it from reading the literature is that people suspect that there's only 2 of them. And hopefully at the end, if I'm wrong about that, please chime up and let me know that I am mistaken if there is a known to be 3rd one. It's just even, you can do a lot of exhaustive numerical searches and be pretty confident about the answer, but if you don't actually have a proof, that still is a bit unsettling. All right, so on the new stuff, onto kind of a hybrid of these ideas called mutually unbiased equiangular type frames, MUETFs. And what this is going to be is like MUB, what I want is a bunch of bases, now going to be frames, that are mutually unbiased with respect to each other. But instead of having each individual frame be an orthonormal basis, I want it to be an ETF for its space. And so if you fix the M parameter and you vary the N parameter, notice what I'm getting here is the modulus squared of the Welch bound. And so what I'm having is a bunch of ETFs, all with the same D and N parameters. But what I want is this extra special property that when you take any one of the vectors from one ETF and any second vector from a second ETF, and you take the dot product of the two of them, take the modulus of that, what you get is something that has constant modulus. And it turns out that that modulus is actually 1 over D. Okay, you can apply proto-Gerson in this case and show that if these mutually unbiased ETFs, M mutually unbiased ETFs of parameters Dn, if they all exist, then you get this bound between M, D, and N. And it's kind of nice because it unifies the two other Gerson bounds. When you pick M equal 1, this reduces to the classical Gerson bound on the maximal number of equiangular lines. When you pick N equal D, this reduces to the maximal number of MUBs you can have in D-dimensional space. Here's an example of one. This is actually done with a second student, with Courtney Schmitt. And if you're listening, Courtney, hi. So what we have here at the top are actually 3 mutually unbiased ETF 4-5s. Each one individually is a complex regular simplex in 4-dimensional space. And I put them next to each other, and you can see what I have below is the gram matrix. Notice this nice pattern on the diagonal. All of those are the gram matrices of regular simplices. Now on the off diagonal, I'm getting something pretty remarkable. I'm getting something of constant modulus. Turns out that they all have modulus 2. Actually, sorry, 1/2 once I factor in the 1/4 out here. And so it's like, that seems like a miracle that that thing even does exist. Yeah, it is, kind of. They're very, very rare. But what I want to convince you of is that they are worth looking for. Because if you can find them, then you can build ETFs from them. So Ben and I, this is actually from December, but it was published, put on the archive this year. Yeah, nothing great has happened in 2020. This is actually from 2019. And so what we have is one ETF, and then I have this paired up mutually unbiased ETF. And notice that with this, the number of mutually unbiased ETFs I have actually equals the number of vectors in the first ETF. So I got 2 ingredients here, one ETF and a mutually unbiased ETF with second parameters where the number of them equals the number of vectors in the first. And I need these parameters to meet this condition. And I'll explain that condition coming up. But if you have that, then you can do this ludicrously dumb construction of an ETF, where it's just a tensor product construction. Going back to 2003, going back to the early days when quantum people were nice enough to share some ideas with me, the first thing they said is, hey, there's this way you can tensor up MUBs with each other and make other MUBs, and that's not going to work to make SIC-POVMs. And that is exactly right. But remarkably, there is this way that you can tensor some ETFs with other mutually unbiased ETFs to make a bigger ETF. So for example, on that previous slide, I gave you 3 mutually unbiased 4x5 ETFs, regular simplices in 4-dimensional complex space. And, oh, I have 3 of them. Can I also take an ETF with 3 vectors in it? Yeah, I can take the Mercedes-Benz, the 2x3 regular simplex in R2 if I want. So I got 3 frame vectors, I got 3 mutually unbiased ETFs, and they satisfy this parameter relationship. When I work out either side of this equation, I get 1/4. And so I can take the first feed, tensor it with the first side, the second feed, tensor it with the second side, the third feed, tensor with the third side. Each one of those is a 2x1 tensored with a 4x5. So each one of them is an 8x5. And I put them next to each other, and what I get down here is then an 8x15. And it turns out that that's going to be an ETF. Now that ETF is known, and actually this construction of it was actually known, but very, very hidden in that particular system. I'll talk more about that in a bit. But what works here is, so if I kind of take
any of the two vectors from sort of the first block and inner product them with each other, well, the inner product of phi1 with phi1 is just 1, and then I'm left with an inner product of two members from this same member of 3 mutually unbiased ETFs, and so I get a certain value. I get 1/4, turns out. Meanwhile, if I take inner products between guys in the first block and ones of the second block, well, I get an inner product of phi1 with phi2, which is a half, and times an inner product of something from psi1 with something from psi2, which turns out to have modulus 1/2 as well. And the product of those two is 1/4. And so a miracle happens. It happens to be the same value that you get here for this inner product. And so what you get are new ETFs, which you get, well, not new at this point, but I'm trying to convince you that eventually, if you do this right, you're going to get some new ETFs out of this. So you get new optimal projective packings. Okay. So it gets pretty technical from this point forward. And in the interest of time, I'm not going to go into too much of these details. But for those of you that are familiar with the literature, you'll know a lot of these ingredients. One of the basic things that frame theorists that grew up in harmonic analysis, like myself, we do is we look at what are called harmonic frames. What we do is we take a character table of a group, we take a discrete Fourier transform matrix or its adjoint, and we pull rows out from it. And we do that because when you do that, you automatically get something that's tight, and you automatically get something where all the columns have equal norm. And so the problem just becomes, well, let's try to pull out the right rows so that the columns have a nice pattern of inner products. And these are called harmonic frames. And when you take the inner product between two of those restricted characters, it turns out that what you get is something that's expressible in terms of the discrete Fourier transform of the characteristic function of the rows that you extracted. And because I'm only interested in the modulus of inner products, you get a modulus squared of that Fourier transform. And the Fourier transform interacts well with modulus squareds because it's a pointwise times your conjugate. So I can actually write that as the Fourier transform of the autocorrelation of the characteristic function of D. And so when you have a harmonic frame, the entries of its Graham matrix are related to this function, the autocorrelation function of the characteristic function of D, which turns out to count the overlap between D and shifts of itself, which when you establish certain injection between this set and this set, actually counts up the number of times a member of your group could be written as a difference of members of the set that indicates which rows of the character table you pulled out. And so, so then what that leads you to is the field of combinatorial designs, which has thought about such objects quite a bit. You can talk about what's called relative difference sets. And what a relative difference set is a subset of a group, like for example, down here I have 1, 2, 8, 4 as a subset of a group of Z mod 15. And what I want is that when I take differences of members of that group with each other, of course I'm going to get some zeros. 1 minus 1 is 0, 2 minus 2 is 0, etc. But what I want is a nice pattern elsewise. And in particular for a relative difference set, there is this thing that's called the H, that is going to be what's called the forbidden subgroup of G. And anything in the forbidden subgroup, which in this example is 0, 5, 10, I don't want to show up here at all. It should not appear as a difference. In other words, no two members of my subset D should differ from each other by a member of H. They should all be in different cosets of H. And notice neither 0, 5, or 10 shows up down here. But moreover, anything that is not in that subgroup, of which there are 15 members of the group, there are 3 in that subgroup, there are 12 things that are not in that subgroup, every one of them should show up the same number of times. In this case, they should show up exactly once. And you see 1, 1, 1, 2, 1, 3, 1, 4, etc. in there. No 5 because it's forbidden, 1 and 6, etc. And so it turns out that if you do that construction, you can actually build MUETFs from it. And then you can combine them with ETFs to make new ETFs. I will say before moving on, there are basically 2 known constructions of relative difference sets. This one was sort of an example of the one I'm going to be using quite a bit coming up in just a minute. This other one is sort of a different type. There's some equality in the parameters here. And it turns out for this one of second type that it actually does also lead to MUETFs, but only in the special case of mutually unbiased bases. And so you can actually build MUBs using this approach. And I was like, oh, that's too natural to not be observed before when I ran into that observation. And yet you look in the literature and it comes right out. You look at generating MUBs from relative difference sets. And the first hit you're going to get on Google is this great paper from Godsell and Roy from '09. In general, Ben and I were able to prove this equivalence. This is not a deep result. You basically just write everything down and everything works. And it says, hey, if you give me a relative difference set and you pull out the rows of a character table corresponding to it, that's going to exactly correspond to when you get an MUETF. The rows you pull out have to be corresponding to a relative difference set. Now, how do you index the columns? Well, it turns out you have to index the columns according to what's called the annihilator of the group that the row indices were relative to. So there's a group structure in the columns as well. And when you put this together, this actually unites a number of classical results, and, like the classical equivalence, not that classical, but the traditional equivalence between ETFs and difference sets, that's here, and also this result of Godsell and Roy. They both fit under that common framework. Now, in and of itself, that's just, oh, that's a cute observation, but what good is it? But when you lift it up to being able to build new ETFs, it becomes kind of interesting. Because we can take this classical construction of relative difference sets. This goes all the way back to Gordon, Mills, and Welch. And yes, this is the same Welch as in the Welch bound, but this is from a decade before he did the Welch bound. And what they did was they took something called the Singer difference set, and they factored it in terms of this other object that was a relative difference set. And so there's this infinite family of them that exists for any prime power and integer q greater than or integer j greater than or equal to 2. And if you take those sort of off-the-shelf relative difference sets and you tensor them up with off-the-shelf ETFs, then you get other ETFs. And it turns out that a lot of them are new. Now, if you really dig carefully into the Gordon, Mills, and Welch construction, which we do in the paper, by the way, this is all up in a paper on arXiv if you want to see any of the details of this, you see that the tensor product construction is really implicit in there. That what Gordon, Mills, and Welch are really saying is that the harmonic ETF that arises from the complement of certain Singer difference sets can be achieved by taking a tensor product of another ETF of that type and mutually unbiased ETFs that arise from a relative difference set that they discovered. And so just to give you an example of the power of this, I'm going to give you a new infinite family of ETFs that arises from a single ETF, from the ETF 3.9 that I had up earlier. And to be clear, there's actually an infinite number of ETFs that you could use as your starting point here that seemingly, from all we've been able to tell, generate new infinite families. So this is a new infinite family for each one arising from a single infinite family. Yes, it's still infinite. So what you do in this case is take the ETF 3.9 and then actually take what we call the Naimark complement of this. For any ETF dn, there's a natural construction of an ETF n minus dn. And what you get is an ETF 6.9. And this number that for the compatibility condition of the tensor product construction needed to be a prime power, it turns out to be a prime power. And so you can build the requisite relative difference sets from them. You can build the requisite mutually unbiased ETFs. You can then tensor them with ETF 6.9. And what you get is this new infinite family of ETFs. Now they get big in a hurry. The first one's pretty small. It's an ETF 96,153. After that, they get enormous. When you take Naimark complements of them again, they become a little more recognizable. You get ETF 57,153. That's not very small, but it's amongst the smallest that have been discovered in the last few years, especially when you exclude the SIC-POVM literature. And it's always kind of difficult when you talk about what means small ETF. Are you talking about D being small or N being small? Or in this case, I'm talking about N being small. Under that criterion, it might be the smallest new one discovered in maybe, I don't know, 5 years or something like that. I might be overemphasizing it, but it's pretty small. And if you do a similar construction starting with ETF 10, 16, it gets small as well. Anyway, so it's kind of cute. It's basically a very dumb construction with a very sophisticated ingredients. MUETFs are very neat, very rare, it seems. But the construction itself, once you have them, is pretty simple. So just to sum up, ETFs and MUBs are different types of optimal projective codes, optimal projective packings. You can think about this MUETF idea as a unification and generalization of ETFs and MUBs into a common framework. You get a single Curzon bound, you get a single difference set equivalence. But more importantly, MUETFs give you a way of building ETFs. And that would be academic if we didn't know how to build MUETFs, but we do. We have at least one construction from relative difference sets. I would really like to have more constructions of them, because if we can find more, then we might be able to find new ETFs. I will point out that what we're really looking for is MUETFs that are not MUBs. Turns out the tensor product construction in that case just generates more stuff that are MUBs. I will say there, though, and those we already know what those are, but in the non-MUB case, the only MUETFs that we can find, they have all been complex. And that's interesting because with MUBs, we know we can build them to be real, and they do not have to be constructed harmonically. You can do tensor products, and you can have a construction from mutually orthogonal Latin squares. Does any of that stuff generalize to be able to actually build, hopefully, real MUETFs? I don't know. I would really like to know the answer on that. I will say that the relative difference set literature is not going to offer a lot of other options here, because beyond the ones that generate MUBs and the ones I've already shown you, the relative difference set literature gives you exactly one more example. Whereas the Gordon-Mills Welch construction will give you 3 mutually unbiased 16 by 21 ETFs. There is one more example from the RDS literature that gives you 6 of them. And so I think if we're going to try to find these guys, we have to look somewhere other than the relative difference set literature. All right, thank you very much.
Thanks, Matt.